once around Trappist-1. So Trappist-1 is a star that lies in the constellation of Aquarius. It's very, very dim. Magnitude 18.8, way beyond the capacity of most amateur telescopes, in fact. And the reason for that is actually the power of the star is very low. It only puts out 1/2000th of the energy that our sun does. This is a very dim, very faint star indeed. And it's very close to the blue line, which is the ecliptic, the path of the projection of the sun onto the night sky as the Earth orbits around, roughly the plane in which we find all the planets of our solar system, with the solar system being basically a flat disk. And the position of Trappist-1 marked by that red circle, of course. Discovered in 1999 by John Gizish and his team, who were doing a survey of ultra-cool red dwarf stars using the La Silla telescope in Chile. And this star is so faint, as described, that it doesn't appear in most catalogues. So this doesn't have another catalogue designation. Trappist, as in Trappist-1, well, that's an acronym standing for the Transiting Planets and Planetesimals Small Telescope. Very contrived indeed. You have to have a good acronym in astronomy, it seems. And this is in fact two telescopes, both 24-inch reflecting telescopes, 600 millimeters, one in Chile, one in Morocco. And it was the one in Chile that was being used for this particular discovery. And it was looking for the dip in the light caused by a planet transiting across the face of the star, blocking out some of the starlight. You see a slight dip. Now, we've worked out that this star is one of the sun's near neighbours, 40.6 light years away, using the usual methods of parallax. And well, we wouldn't have discovered it if it was any further away. It's so faint. It's an M8 class red dwarf. These letter and number categories will go O, B, A, F, G, K, M, through the order of decreasing temperature from the blue hot stars at the O end through the white and yellow stars in the middle, the orange and red stars K and M. So if it's M, it's red. But that doesn't necessarily mean it's a small star. You can have red giants, and they will also be class M. The number after the letter is a subdivision within the class. So M0 is the hottest, and M9 would be the faintest within the red category, and so forth. So our sun, I think, is G2. This one's an M8, which puts it right at the far end of the cool side of the red dwarfs. An M9 would be the extreme case. And the reason this is so faint and cool is because it's just 9% of the mass of our sun, only just large enough to be a proper star. The ultimate would be around 7.5. That's percent of the mass of the sun. That would be the lower limit for a proper star, and such a star would be an M9. In fact, in radius, it's only just larger than Jupiter, a little bit larger. The mass comes to give it a much more dense core in the center and just a slightly larger volume. Now, I said it was cool, temperature just 2,566 Kelvin. So that's very cold indeed. We tend to reckon that 3,000 corresponds to a sort of red hot object. So this is nearly 500 degrees cooler than that. And because it's cooler, you can actually have molecules persisting in the outer layer of the star, the photosphere, things like carbon monoxide, water, and so forth. And you can see those in the spectrum of the star. But most of the energy, most of the electromagnetic radiation coming from the star is in the form of infrared. The peak in the spectrum is so far shifted down to the longer wavelength end that only a tiny fraction of the light comes out as visible. That's really why it's so faint to our eyes and looking through telescopes. And an infrared telescope is definitely the way to go in terms of studying this. It's older than the sun, 7.6 billion years, so 3 billion years older than the sun. But there's an important fact about such very small stars is that they spend a long time in their protostar phase, their pre-main sequence phase, before they eventually reorganize themselves and get hot enough and dense enough in the core to kick off nuclear fusion. And that, for such a small star, can last around 2 billion years. For a star like the sun, it probably only takes 100 million years, something like that, so much, much more rapid. But then with a larger star like the sun, everything is more rapid. The sun's going to live around 10 billion years in total and is about halfway through. Trappist 1, well, 1,000 times longer, 10 trillion years. And so that 7.6 billion is a tiny fraction. In terms of what attracted everyone's attention, it was when they saw the light curve, the plot of the amount of light coming from the star over time running horizontally. And you can see 1.0 is the typical slightly noisy band of star activity. And then there are a pattern of significant sudden drops in the light. And analysis of those shows that equally deep drops occur with equal frequency. And the first two here, 1b and 1c, are labeled up for you. You can see that pattern has been identified. They were the first of 2 planets to be discovered in 2016, and then the following year 5 more. And we have the dips in high resolution for all of those planets, B, C, D, E, F, G, and H. And you can see the dips, they're quite a small percentage of the overall light. So these are small planets. You can see the periods of the orbits there from 1.5 days for Trappist 1b, 2.4 for the next one, and so on. And the last one there is labeled 14 to 25 on that particular graph. We now know the answer is just under 19, in fact, in the middle of that range that was given. But these high resolution plots tell you quite a lot. You can see they get wider as you go down. That's because the planet is orbiting more slowly and therefore takes longer to cross the disk of the star. You can see that the steepness of the shoulder of the dip gradually flattens out, again representing the speed with which the planet crosses the edge of the star. But it also tells you a little bit about the size of the planet. And you can work that out in various ways. Obviously, just a matter of using the formula pi r squared for the surface area of the disk of the planet and the star, and the amount of light that's been blocked in the middle. And you can do other calculations along the same lines and work out quite a lot from this sort of information. So we have quite an amazing data table on these planets, ranging, as I said, from 1.5 days orbit at just 1% or so of the distance between the sun and the Earth, the astronomical unit, going out to planet H with an 18.76 day orbit at 6% of an AU. You can see the radius of the planet and the masses of the planets, and well, they're all fairly similar to the radius of Earth and similar in mass. A couple of them there just down to 1/3 the mass of the Earth. And their densities, well, we can see those, and their surface gravity. We'll have a look at them individually. It will be more interesting that way. In terms of their orbits, this is a tiny system. It's a little bit larger than the orbits of the moons of Jupiter around Jupiter, but it's a lot smaller than even the orbit of Mercury. There is a sort of inset plot that you can look at showing B through H all fitting in a tiny ring around where the orbit of Mercury would be much, much larger. Perhaps this shows it again. We've got the inner solar system marked out with its habitable zone, with Venus on the inside edge of that, Earth in the middle, and Mars on the outside edge, that green zone. And in the plot at the top, you can see enlarged 25 times the Trappist 1 system. And those E, F, and G planets are very interesting because they're in the habitable zone in their system. D also, perhaps, because it's just on the inner edge and it's a rather smaller planet, and the planet's size should be taken into consideration as well. Another way of plotting this is to look at the amount of heat coming from the star, and we've got that along the horizontal axis. So you've got hot at the left and cold at the right, and you can see that the planets are lined up in order from the star: B, C, D, E, F, G, H. The size of the disk shows you their size, their vertical position shows you the density of the planets, and the dotted lines are for comparison with the Earth, Mars, Venus, Mercury, and our moon. And so the ones that are nearest to the Earth's conditions are definitely D and E here. D, a little bit more illumination, a little bit smaller planet. E, a little bit less illumination, and again, slightly smaller. And then we have the slightly larger F and G planets that are getting less heat. So let's have a look at them individually and work our way through. So Trappist 1b, 137% the mass and just 1.12 times the Earth's radius. Rocky planet, 4 grams per cubic centimeter. The innermost of the planets getting 4 times the heat energy, and the James Webb Space Telescope was able to measure the surface temperature of planet B at 500 Kelvin. So that's pretty warm indeed. That's well over 200 degrees centigrade. And so it's going to be far too hot. Also, being so close in to the star, it's likely that this is suffering a degree of the same effect that Io suffers, the moon of Jupiter, the tidal squeezing effect, causing it to heat itself up from the inside out. And so this is likely to be an extremely volcanic place indeed, and thoroughly nasty. Trappist 1c moving out, again, just a little bigger than the Earth, likely to be rocky, 5 grams per cubic centimeter. The heat, well, that's double the heat energy that Earth receives. We think it's got a carbon dioxide atmosphere, and again, that's going to boost the temperature. And James Webb measured that as 380 Kelvin, so around 100 degrees centigrade. And so this is certainly boiling hot, too hot for liquid water in all probability. Moving out to D, things get interesting. This is 40% the mass of the Earth, and a little bit less dense, but still rocky, 4.3 grams per cubic centimeter. But it gets almost the exact same amount of heat energy that the Earth does, 104% to be precise. And of that radiant energy coming, only 1% is in the visible light band. That's fascinating. So this might be a warm planet on the inner edge of the habitable zone, but it's going to be pretty dim. Trappist 1e, slightly smaller than the Earth, again rocky, 4.9 grams per cubic centimeter. Gravity just 8/10 that of the Earth. Heat, 60% of the heat flow coming to it from the star. So the temperature there, with a little bit of a boost from any atmosphere, is very, very likely to put this in a condition where it can have liquid water pooling and forming oceans on the surface, and potentially habitable. Same is true for planet F. It's almost an Earth twin. The mass, the radius, the surface gravity are all just like Earth. Baseline temperature without any greenhouse effect, 217 Kelvin minus 55 C. In fact, for Earth, that corresponding figure would be 40 C if we did not have an atmosphere. So if this has an atmosphere with a greenhouse effect, it could bring that up to a nice sort of above freezing temperature, and again could well have a liquid water ocean as shown in the artist's impression at the top there. Planet G, well, Also, a little bit bigger than the Earth, a little bit more massive. Density suggests rocky at 5 grams per cubic centimetre. Gravity very similar. Baseline temperature a bit cooler now, minus 73 C, 200 Kelvin. And again, boost that with a greenhouse effect. Have to have quite a thick atmosphere to make this capable of supporting liquid water. But the Hubble Space Telescope did detect water in 2017, but that was probably water in the atmosphere rather than on the surface as liquid. So this is probably water vapor in a thin atmosphere. And it's going to be fascinating because I think we're going to learn a lot more about these planets as the James Webb Telescope turns its attention to all of these individually. Finally, Trappist 1H, well, it's a little bit smaller, 33% the mass, 3/4 of the diameter, and the surface gravity, well, 103% that of the Earth. Now, this is beyond the habitable zone. It's only getting 13% of the heat. And so this is going to mean that even with a bit of atmospheric boost, we're talking about an ice world with conditions similar to those right at the south pole of the Earth over the whole planet. So there's a whole gradation of these planets. And of course, the thing that everyone is interested in is whether or not any of these have life. And the statement, I think, has to be that it might be possible, with Trappist 1e perhaps being the best candidate, maybe D, maybe F, maybe all three of them. But there's a number of factors to think about that are going to affect all of this. These planets are in an orbital resonance with each other, very similar to the way that the moons of Jupiter are in orbital resonance. And they're also very close to each other. And so there are likely to be significant tidal interactions, both with each other and with the star. And so that is going to affect things. I've already said that planet B is probably going to be getting squeezed and stretched enough to cause huge amounts of volcanism, making it extremely unpleasant, as with Io at Jupiter. We've got the fact that the star is putting out heat energy, infrared radiation, but very little light indeed. So very dim in the optical part, not much chance really of photosynthesis. The visible photons are used by plants because they carry enough energy to allow the plants to extract the energy by photosynthesis and do useful chemistry. And infrared photons really aren't very good for that. They don't carry enough oomph. But that doesn't mean that you couldn't derive your energy, as many bacterial species do on Earth, from a chemotrophic source. They use the pure chemistry of the rocks, the iron and the sulfur in rocks, and combining those with each other and or with native hydrogen to extract energy, rather than getting it from a light source. They get it from a chemical source. It also means perhaps that any creatures running around on the surface are likely to be blind. What would be the point of evolving eyes when your planet, even at planet D, is so dim as to really not do you very much good at all? Of course, any vision is better than none, and we're being very parochial. Maybe they found a way to do all of these things with the abundant infrared radiation. The other factor with these red dwarf stars is that they do have a nasty habit of erupting with significant stellar flares. And those flares can pump out a lot of harmful radiation, a lot of ultraviolet light, X-rays even. And that's obviously bad for any life. So you are going to need some protection. Now, an atmosphere will protect you for a while, but it will get ablated by it and will get blasted away into space. And you're better off actually having a magnetic field. And a magnetic field usually means a conducting iron core, which most of these planets probably have, being rocky planets, and rotating at a reasonable rate, which we don't know. and it's quite possible that their rotation is tidally locked, jumping to the last point there, such that they keep one face towards the star, certainly for the innermost ones. And that might change things, because it might mean that you have a hot side and a cold side, and unless you've got a thick atmosphere like Venus to spread the heat equally around everywhere, then maybe there's a temperate zone on or near the day-night boundary. So conditions could vary quite significantly across the face of the planets. So again, until we understand whether these are tidally locked or in some other strange rotational situation, there are a number of unknowns that could affect things. The other factor, I mentioned that it takes 2 billion years for a star like TRAPPIST-1 to calm down from its formation into its stable main sequence state, the protostar phase. And as it does that, it's likely to be very much more active with flares. They take a long time to calm down to an even reasonably sustainable rate. And so conditions near to the star can be very bad for an extended period of time during that early stage. That probably happened in the solar system for the first 50, 100, 150 million years of the existence of the Earth. But of course, at that stage, the Earth was probably a ball of molten lava anyway from its formation phase. And so didn't have liquid water oceans. Those were all delivered later by subsequent asteroid and comet impacts and other methods. And so it became habitable, and by then the sun had calmed down anyway. But the balance of things here may be different, and it could be that the water is delivered during those first 2 billion years, but the star is so rowdy that it doesn't really bode well for the early evolutionary phases of life, and maybe the water gets blasted away. I think a lot depends on the magnetic field and the rotation, which we just don't know. But there's another factor. We have some evidence that the seeds of life can be delivered to a nascent planet by falling out of the sky. We have samples from the asteroid Bennu here on Earth that we collected with the OSIRIS-REx mission that revealed the presence not only of 20 different amino acids, but all the building blocks of DNA, the A, C, T, G, and even the U of RNA, the nucleotide bases, in the material from Bennu. And so if organic chemicals like that can form on small bodies and in space dust and so forth, and then rain out on the planet, well, it's going to rain out on all these planets as well. And so it's entirely possible that the seeds of life were present on all of them. And they're so close together that impacts and ejecta hurling from one planet can so easily get transferred to another planet. I have a piece of Mars in my meteorite collection that was blasted off the surface of Mars a long time ago and fell to Earth. And if that happened, then perhaps bits of Earth have also landed on Mars, and each planet has thoroughly contaminated the other as a result. So maybe if life could get a toehold, I don't know, on planet G or even planet H, farther from the star during the early phases, it could rock hop from one to another as the star calmed down. So there are possibilities here. And well, I just hope we get to find out while I'm still around to know the answer. I'd be absolutely fascinated. So how about spending your time on a cruise interstellar, going and visiting, or even just sending a rocket space probe to go and have a look? Well, 40 light years is a long way. It is too far for any rocket technology that we have today. Even our fastest space probes would take hundreds of thousands of years to get that far, so that's not really plausible. The Breakthrough Starshot project, where they're going to use a laser on Earth to power a little tiny star chip spacecraft with a solar sail or a laser sail to try and accelerate to a goodly fraction of the speed of light, that would still take 200 years to do the distance. And then we need another 40 to get the signal to come home. So again, this is really too far for this sort of exploration in any technology that we have, or even have dreamt of reasonable chance of building in the next 50 years or so. So we've got to look at these planets remotely, and of course we can do our search for extraterrestrial intelligence, the SETI approach, looking for laser signals, radio signals, light, anything that we can detect, and trying to determine whether there is anything abnormal about it that doesn't have a natural origin but is artificial in nature. And so far, nothing. A couple of major searches of TRAPPIST-1 were done in 2017 and 2024, and we haven't found anything there, but then we haven't found anything else anywhere else either. So it just may be that we are alone, or that we are not looking in the right way, or that our technology is not up to it yet, or that these civilizations are just not putting out signals anywhere that we happen to have looked. But in 2,000 years' time, such is the wobble of the path of the Earth around the Sun, that we will become a transiting planet as viewed from TRAPPIST-1. Any astronomers on any of those planets looking back towards the Sun will see dips in the light curve once a year caused by the Earth passing in front of Sol, and they will be able to infer the existence of the planet Earth and see that it is just like their home world, perhaps. And maybe they will turn powerful telescopes to us, radio telescopes, and be able to pick up evidence that we are there. So maybe they will find us before we find them. Wouldn't that be interesting? And I'll just finish with this little poster that was produced of the potential for people planet hopping on a cruise in some sort of starship and going and visiting TRAPPIST-1 and looking out the window and in wonder at the amazing worlds of the TRAPPIST system. So thanks very much for listening, and I hope you've enjoyed that one. Bye for now.